Well, thank you for the invitation to be here. Move these. I know they want me to stay here. You're taping. So what I want to do today is to tell you, I'll do things the opposite way you normally do things. And thank you all for coming. I see even people came here in from Guiyang, China to come and hear this talk. I'm really honored. Thank you for coming. It's a long trip from there. But usually you give a talk and you tell about all the wonderful things you found and what it means. You thank everyone for coming and you go out and that's it. So I'm going to do the opposite. I'm going to tell you what I don't know. So I'll give you a couple of subject areas and I'll take you to the point where this will tell you, we don't know this. And there are all these, we don't know this. It's not some little thing like, where did I put my car keys or something. It's going to be the big areas where we just don't know very large amounts with very big questions hanging out there. So I'll show you some data that's new, unpublished, and towards the end, and that we don't understand, but we have a theory for it. And I reserve the right to change that theory in a week if I have to. So I'll tell you what we know now and what it means. So I started off with showing this picture of isotopes to remind me that I'm going to talk about isotopes. And you can see hydrogen, deuterium, and tritium. I'm obliged to do this. When I came as a child to UCSD as an assistant professor, I inherited a laboratory of a famous isotope guy named Harold Urey, who discovered these two isotopes and won the Nobel Prize. All the measurements are done in Urey Hall, and so I thought it appropriate to start that way. Those of you who are meteorite persons or isotope persons know the name, so that was where I started. So the questions are going to go across time scales. So I'm going to do this. There's logic to my madness that it's going to be done basically through time, starting from an older time, before the planets have formed, going to that part where things are in between to when the Earth is formed, and then through the history of the Earth record to today. It'll be in pieces where we measure parts of it to ask those different questions, but at each step of the way we'll be using an isotope trick to measure things and to say something about what happened, not necessarily the final word, but a word or a perspective on it. And I'll be sure to point out what I don't know for sure, which is a lot. I'm going to start with sulfur isotopes. There's 4 stable isotopes. And I'm going to show you in a minute, but there's all these rules for how you change isotope ratios. And if you're an electronics person, if you can build a circuit and measure as a ratio, you can always do it better. And the only way you can do it better than that is to measure a ratio of a ratio. Then you have a cancellation of errors. All electronic circuits, that's the trick for getting rid of electronic noise. Measure it as a ratio. When you look at the circuit diagrams in your mass spectrometers, you see all these circuits that are going in there that are expressing as ratios because you null out noise. Okay, so when you deviate then in these isotope ratios from the normal rules, where it all depends on mass, which is what it used to be, we call it this delta. So delta equals to 0 means it's normal, right? I give my colleagues in the physics department and chemistry department little delta symbols. And so if you get a delta equal to 0, you're normal. And if you get a delta equals to 10, it means, you better go work with the engineers. So the delta equals 0 is normal. And so sulfur's in the meteorites, which are the early record of the solar system. I'll talk about the oxygen story, which is the most important because rocks are mostly made of oxygen. But at the bulk level, one of the few elements that shows up with an anomaly is sulfur. And the question is there a relationship between sulfur and oxygen? And it's small, you see, but if you measure isotopes, you're not impressed at all. But you can see that a number of them are anomalous, especially the urielites, which no one actually really understands where they come from or how they were made. So there's pieces in there, an oldamite, which is a calcium sulfide, which is probably one of the earlier minerals to precipitate out. There's anomalies in there. So the question is, where do they come from? Well, there's all sorts of processes that have been in play. I'm going to talk a bit about photochemistry and just basically in general reactions that give you anomalous behavior that may account for what we see. One of the main gases that you want to think about in a nebula is H2S. These are all important, but that's a good player in a reducing environment filled with an excess of hydrogen. Hydrogen sulfide is not unreasonable, nor is carbonyl sulfide. So we wanted to invest something simple. Is there an isotope effect when you break the bond with a photon of light? Okay, turns out the photons of light you need are in the extreme UV and the hard UV, and the hard UV means energy, but not just the fact that it's hard to get to. So we measured it. We measured it here. This is in the Republic of California and the Republic of Berkeley. This is the synchrotron here, and you can see if you go to AGU, here's San Francisco and the Moscone Center's here. I think it's a leaf blower. And so here's where we do the experiments. You can't use a window when you irradiate a sample with this, so you have to open it straight to the synchrotron and differentially pump your system so that you can keep the gas with no window, because the window will absorb all the UV light below, say, 120 nanometers, which is where we care about things. So we have to build the system and connect it, set it up, and then we do the photolysis as the gas is flowing in the presence of a gold foil. And what happens is, in the presence of a hydrogen-sulfur flow, the atomic oxygen forms a thiol radical that reacts with gold and stays on the surface. This is how atmospheric chemists collect hydrogen sulfide out of the atmosphere, is on gold-plated spheres, small spheres, not big ones. And so we collect the solid sulfur from the photolysis. Simple as it can be. Break the bond, collect it on a gold surface, return it to La Jolla, and measure it. The only hard part is that you only get about 100 nanograms of material to measure, and you have to measure the sulfur isotopes in it, but who said it would be easy? And then this is what it looks like. This is the whole system connected to the synchrotron here, Subratis Chakraborty, the other M Thiemens, looking in to see if it's done right. This is the port, the foil is in here, and so we change the wavelength, and we know exactly what's being photolized. We measure the wavelength of light so we know exactly the wavelength and how much is there, so we can calculate all the quantum mechanics. And then we change the energy so that we hit different potential energy surfaces. This is the wavelength of light that we use in the region, and this is the energy, and we photolyze it. And here's the results. So in this plot, we have an anomalous here, capital delta 33, and a delta 36, which is a 36-32, 33-32 ratio. If everybody was normal, it would sit right here. The error on the measurements is, if you take this and divide it by about 5, that's the error bar in the measurements. All right, so the measurements are, and the experiments are reproducible. So here is 121 nanometers, and you can see it's a large mass-independent effect. Here in this region in red, which I can't quite see, is 90 nanometers. And these are samples that we measured and published in a paper in Science. These are organic sulfur-bearing species that we separated, methane, ethane, propyl, sulfonic acids, from the Murchison meteorites. So what you can see is there's a mass independence that follows some of these wavelengths. So what it means is these organics, at this stage, it's reasonable to say at this level of approximation, these organics were formed by photochemistry, probably in the gas phase, and probably from hydrogen sulfide at multiple wavelengths. 121, that's Lyman alpha, right? That's the main line out of the sun. And the 90 nanometers, we chose these not only to hit different electronic surfaces, but because they're main lines in the solar spectrum. So the evidence at this level right now is that photolysis of hydrogen sulfide gives you something that's not unlike what we see in meteorites. So we're getting our way through there, but part of it that we do for a living is trying to understand this. I live in a chemistry department in the physical chemistry group, so a lot of what, not a lot, but a portion of my group, this is what they really care about, is the quantum mechanics of what happens. And I won't talk about that, and you're probably disappointed, but that's part of what we do. So that gives us a set of what's going on. Why does it give you this anomalous behavior? Why doesn't it do? Normally, this is usually, if you grew up in isotope geochemistry, what you were told was there's a potential energy surface, And the vibrational frequency of the heavy one is here, and the vibrational of the light one here. And the distance from here to here is easier to break the bond for the light isotope compared to the heavier because it's closer to the dissociation energy. This is a total fairy tale. It has absolutely nothing to do with the way a bond breaks. It's not as though one starts warming it up and it climbs up this little ladder here and then boom, it hits a dissociation and breaks apart. That's not how any dissociation works in the gas phase. It's all a complicated matter of crossing curves. And you have to solve three different parts of the equation with the Schrodinger equation and then the time-dependent Schrodinger equation, which is the worst one of all because you have to deal with the off-diagonal elements in the matrices when you solve the equations. So it's really nasty stuff that happens. And in the end, you cannot, I'll tell you this, the state of the art in quantum chemistry is not sufficiently precise enough to allow you to calculate an isotope effect. It cannot be done because there's not enough computational power to do it. So for the first time, this community is guiding people in quantum chemistry and quantum physics because the isotope results tell them things you can't learn from spectroscopy. In the old days, it was us taking things from people like Yuri and Bigeliason and Mayer and Mark Javois and taking a lot of their work and applying it. But now it's the other way around. We're able to measure things, we meaning the community, not necessarily me, and do new chemical physics because you can see these sorts of transitions occurring at the isotope level, but you can't see it otherwise. So that means that there is a role, at least in this part, in the early nebula, that's photochemical. Then the question is, where else might it show up? And as I said, here's the solar spectrum at 90, 121, and 130. Some of these have lines. There's structure in the spectra. So we're working our way through these to understand not only the physics, but what can we say about the early solar system when this might be going on, where the photolysis occurs. But, you know, theories are wrong. This is a theory. This is my favorite one. This shows why the dinosaurs were extinct. We all think about the KT boundary or the KPG boundary and extinction due to that, but now we know from evidence in the record that the dinosaurs died from smoking cigarettes. Okay, now what was I talking about? Okay, so now in the sulfur, it's now known, and this goes back to a paper James Farquhar and Weiming Bao did in my laboratory some 14 years ago, that in the Earth's earliest record, sulfur is isotopically anomalous. It's also known that the anomaly comes from SO2 photolysis. But here's the important part. If you're an atmospheric chemist, you know today that SO2 does not photolyze. And that's because the wavelength of light you need is less than 249 nanometers. And 249 nanometers is a magic wavelength because that's where ozone absorbs. So the ozone layer removes that light. It does not get into the troposphere. A little leaks through the atmosphere to get to people like me that have fair hair and light skin to give us skin cancer. But most of it doesn't get through because of that. So when we found this in a Martian meteorite, the idea was if the Earth did not have oxygen, it didn't have ozone. If it didn't have ozone, the UV light should come down to the troposphere, ground level, and photolyze SO2 and give us this anomalous fractionation. In which case, that means that everything should be normal. Here's today and here's 2.2 billion years ago, but here's the early Earth. So what it means is in this record, and now there's thousands of measurements. Pierre's not here today, I don't think. Oh, there he is. Pierre's one of the culprits for filling in all this and making it even more complicated because the SO2 photolyzes by this UV light because there's no ozone. There's no oxygen. Otherwise, you would not be able to get the anomaly because SO2 doesn't make it into the stratosphere. It's limited by rainouts, so its lifetime in the atmosphere is 5 days. So then you acquire this anomaly, and what you're measuring here is essentially the origin of oxygen and ozone through the archean. What we don't know is there structure in here? What we don't know well enough, and there's at least 3 or 4 of you in the audience thinking about this, is how is it stored in the mantle? Where does it go in the mantle? What's the lifetime in the mantle? How is it brought back to the surface? All from this anomaly produced in the atmosphere. So the important part is that it measures ozone and oxygen. And when the banded irons form here, we know the oxygen level comes away, boom, no UV light at ground level. So you have a way to measure what's going on in the archean, presuming that it all comes from SO2 photolysis. So that's sort of, it's a summary of what we think today, but it doesn't mean we all agree. There's a lot of parts of this, and they're all interesting, and there's a lot of new geochemistry and geophysics that people are getting out of digging at this sulfur sample based on the effect that you have a source of an anomaly that you can use to follow the origin and evolution of life. Part of it, though, gets complicated because SO2, so it's based on the assumption it's all SO2 and there's no ozone protecting it in the environment, and the ozone layer is here. Here's 25 kilometers, here's ground level where plants and animals and people live. And then the tropopause is somewhere about 10. So SO2 doesn't get up into the top of the atmosphere. Except we learn a little bit more in nature because volcanoes emit SO2. And the big ones get SO2 into the stratosphere. And one of the weakest, one big link, we just wrote a paper 5 days ago, turned it in, that shows that if you put enough sulfate into the upper stratosphere from SO2, or if you have alien or fugitive SO2 getting into the stratosphere, it makes sulfate. But sulfate's white. And white up here means it reflects light. It cools the earth, right? So the famous year of no summer was cold because in part black carbon, but also because you had a lot of sulfate reflecting away visible light. The earth cools. So if now, and it may be the case, and I'm going to show you that we have more sulfate up here than we expect, it means the earth is actually, if we took that sulfate away, it means the earth would get warmer. Because right now, it's reflecting some of the heat. It's hiding the global warming, in other words. So we need to understand the detail of what goes on up here to understand what's going on down here. And the sulfur isotope anomalies today, as you'll see from volcanoes, shows up in the record. So we can use that same sulfur anomaly to understand what's happened over time up to today. And the Earth, as it turns out, the idea that you could perturb the whole stratosphere from small events seems impossible, but it's not. The atmosphere is so tiny by comparison to the planet, it's easy to mess it up. So what we did was, we've done this twice, and we've done it in Greenland once, gone to the South Pole, and dug a pit. This is a picture of my graduate student, this is me, that's the South Pole, and if you look, there's little poles back here that are the former South Poles. The whole Antarctic ice sheet moves about 10 meters a year. So this was the year when I was there, that was the South Pole, and then the year before it was here, and the year before it was here. You have a nice even deposition record. So what we did was dig a snow pit and of some 30 tons to take a high time resolution. So rather than going back through deep time, go through year time, but get high resolution to see what happens in nature. This was a picture that I won, but I haven't collected $100. A friend of mine in the biology department told me, Mark, we made the cover of PNAS. I said, and I looked it up, I said, no, you didn't. It's a frog, man. You didn't make the cover, it's a frog. He says, yeah, but it's my frog. I said, but that's not you. You said you made the cover. He says, well, they don't publish anybody's picture on the cover of PNAS. It's a rule. And I said, you know what? I'll bet you $100 that I can get my picture on the cover of PNAS. So this is me taking a picture of the South Pole ceremonial marker. And he hasn't paid yet, but I haven't forgotten it. So this, I did make the cut. This is making, not some stupid frog. Now here's, and this is Joël Savarino. You can see, you're French, so you know that in the South Pole you have to get suited up. In the US is red, but the French South Pole garb that everyone gets is much more splendid. It has colors and everything else instead of looking like a red penguin. It's a nicer outfit. So here we're taking the little records of the elements versus time. Here's where the snow, we take slabs of snow then, this is Joel, of about 3 kilograms, which gives us 6-month resolution. And to dig it, this is halfway down in the stupid snow pit. This is me at the bottom of this, and we had to dig twice as far down to get the high resolution time record. So it's about 28 tons of ice and snow you have to dig. And I have to tell you, I'll just be truthful about this. I'm from Miami. I don't like this snow business. I'm sorry, I know you all ski. When I ski, I'm talking about water, not about snow. So we did it. And it was worth it, now that I can say it's over. So if we look at the anomaly, don't worry about it looking weird. Here's 1983, here's 2003, and let me take the sulfur 36. All right, so you see you have a peak here. 1984, 85, great. It's an El Nino year, there's perturbation, but it's a volcano. Shit. So you can't say much about it because there's a volcano and an El Nino. But then, 1991, another big peak in the record here. Here's a fairly large peak up in the sulfur 33. And you think, okay, so I can diagnose the volcanoes from this. And you do. But it's also an El Nino year, so you can't say anything about the El Nino. But if you go here, 1998, just past it, you have the largest isotopic anomaly in sulfur that you see in the whole record. And there's no volcanoes. But yet, you have a large sulfur anomaly. 1998 was the largest El Nino, it was the largest monsoon in recorded history. And so the question is, what does that have to do with the sulfur anomaly? Because when you look at this, so in the El Nino, after the El Nino, which is like right now, you get La Nina. And what happens is the earth gets cold and dry. And so a lot of the earth in that equator region now, after a year of a lot of warm rain and a lot of growth, it's turned cold and dry. You get wildfires. If you remember 1998, Indonesia and the Amazon all had major fires, all in the equator. That's what the U.S. Weather Department and Weather Channel says, this is an El Nino, but it's not. This guy just calls himself El Nino. That was actually pretty scary from up here. So if you look in the same record, in the soot record, you can see that you have a giant peak in 1998, and that's from the burning. But does it show up at the South Pole? That's the question. So in atmospheric chemistry, the atmospheric chemists are like the isotope geochemists. We argue about everything. Nobody agrees with anyone about anything. About the only damn thing they'll agree upon is biomass burning gives you potassium. It's a good marker of burning. You don't get potassium from volcanoes, but you get it from biomass burning and nothing else. So if I get a peak there, even those guys, that's the smoking gun you have to look for, as they'd say. So here's the potassium. All right, here's La Nina, small La Nina, and then here's the big one. So it's biomass burning that's showing up with a sulfur anomaly. But the problem is, if you have biomass burning at the equator, how does it get into the stratosphere? SO2 shouldn't get into the stratosphere. What's going on? And what I'll show you when I look at the details of the sulfur isotopes, you really need to know this. For people like you all sitting there, I see Pierce, I'll pick on him first, but there's a lot of you. It's one of the parts is when you burn, and volcanoes emit it, you make carbonyl sulfide. And that has an 8-year lifetime. So if you have an 8-year lifetime and you're a gas and you go in the atmosphere, what does it mean? It means you're going to end up in the stratosphere. Nitrous oxide has a 145-year lifetime. CO has about a 5-year lifetime. They all get removed in the stratosphere. So carbonyl sulfide gets to the stratosphere. It gets photolyzed and converted to SO2. So SO2 normally isn't there, but it's a source of SO2 in the upper atmosphere. So it's as though you took an airplane, piped out all the SO2 into the stratosphere to photolyze. So that's important. And you don't need oxygen to photolyze to sulfate. You only need water to do it at OH. So if the carbonyl sulfide at the equator is leaking out, it's a source of SO2 at 26 kilometers, just because the carbonyl sulfide gets removed. So the question is, and I don't know the answer, and there's people in this audience that probably know better, what do volcanoes do? If you look at the emission of volcanoes, this is one of the few papers I could see, that the higher temperature volcanoes emit, this is a ratio of carbonyl sulfide to carbon dioxide from volcanoes. You can see you emit a significant amount of carbonyl sulfide from volcanoes. So what does that mean in the Archean when you had more volcanic activity, especially like 3.9 and 3.8? Carbonyl sulfide is stable, right? That's why it has a long lifetime. In a magma, if you have carbon, water, and reduced sulfur, the end product, unless Bruce Fegley is wrong, and he tells me he's never wrong, carbonyl sulfide is what you get in thermodynamic equilibrium. It's stable. You don't make SO2 unless there's oxygen and a lot of water around. You make carbonyl sulfide. So do I have to worry about that molecule in the Archean? You know, in the atmosphere today, for that biomass burning signal, what's happening is it's going up to the equator, and then in the stratosphere, it transports and oxidizes, and we can see a correlation with the ozone isotopes in the sulfate, that it ends up in the poles by this route. For atmospheric chemistry, this is actually important. It means there's a large source of species in the equator that we don't have in the bookkeeping, because we don't measure much at the equator, and a lot of it gets put into the stratosphere. So it's not in the books, so we don't really know the source of this and how big it is. So if you look in that plot where this is capital delta 36 anomaly and 33, here's normal. And this is basically the Archean line. The green is from that stupid snow pit. And the red are from a series of papers we published in Science and Nature on volcanoes. And you can see they look the same. Except these guys here in the El Nino year don't lie in a cluster. They're more anomalous. If you look at the light that we use here, there's a wavelength dependency in the isotope effect. So it may be that it's the altitude. But if that's the case, that this is an altitude effect that's showing up from what gets up how high, for example, from carbonyl sulfide, that's interesting. We might be able to do something from that. Because, well, I'm going to come back to this. If you plot all of the Archean samples in there, along with the snow pit and all the aerosols, you can see they all sort of lie together. They're all anomalous. But yet, at the same time, we can't account for all of it. And the reason I say that, these are measurements of all the atmospheric particles of sulfate that had been measured as of 2 years ago. And what you see in here is that nobody is normal. Let me say it a different way. All of sulfur in the atmosphere in particles, all of it is isotopically anomalous today, everywhere. It's been measured in France, San Diego, New Mexico, Ohio, Japan, China. We just published papers in China, Tibet, and the South Pole and Greenland. All aerosols are anomalous, not some of them, all of them are. All of the particles in the, and it can't all be from the stratosphere. If you take all the stratospheric sulfate that's anomalous because of the SO2 photolysis, and you put it into the troposphere, you would never notice it. Because the amount that's up there is small by mass. There's just not enough stuff up there that if I put all of this anomalous stuff in with a group of normal stuff, you would never see it unless it was like 1,000 per mil anomaly. And it's not. It's probably 5 to 10 per mil, which we know from balloon sampling. So the question is, what is this? We don't know. So what I said, we don't know. And this is really not something small. Particles in the atmosphere is the biggest uncertainty in climate change. And sulfates are one of the largest compositions, sulfates and carbonates, and they're anomalous. Carbonates are too, by the way. We don't know why they're anomalous. We have an idea. So something is going on in the troposphere that gives you an anomaly, and it looks like the Archean record. So it's not certain what's going on. So what we need to do, the next step, is to go through piece by piece aerosol by aerosol to see what the real range is that we're talking about here and associate it with the climate to see what it means. But I think it probably requires more than one process. And one of the things we don't know, for example, in the archean, which will be interesting, in a dream, what you could pull out of this, we have a wavelength dependency. So if we could look at that, and remind you, this is a time record. So if you go at an age of the sun of 0.1 billion years, here's its spectra from 200 out to 1,000 nanometers. So in this early time period, here and here, early on in the Earth to 2,000 years ago, you have more UV. And it's a part of the more UV light in the early Earth up to, like, say, 1.5 billion years of age to 2, is part of main sequence brightening, right? All stars do it. All one solar mass stars do it. So if part of what we're seeing is a wavelength intensity dependence, and we can do it versus time, we can put together what's the evolution of the sun doing to the archean atmosphere. It's doable. There's a lot of work we would have to do, and we have to get in at the mineral level. But if it really turns out to be like at the South Pole record, that it may be at altitude dependency, which is a UV light dependency, there's a chance to look at stellar evolution in the rock record. It's not totally crazy, maybe 10%, I'll give you that. But it's not impossible. But that's what needs to be done, the combination of the synchrotron and the quantum mechanics and the hardcore mineral by mineral measurements, and the meteorites too, to see if we can get that out. Now, part of it is you have to look at the record a little bit more to see what else you can get to try to interpret this aerosol. So this is, now we fast forward to April of this year. This is Mount Everest. So he decided the South Pole and Greenland was not miserable enough. So we went to Mount Everest on the Tibetan side to collect ice, to look at a record. And so, yeah, it was not so great. One of the things we looked at is radioactive sulfur, which has an 87 day, to try to get an idea of the effect of the atmosphere. And I won't talk about that, the upper atmosphere on the Tibetan plateau. But one of the things we did to try is to go to one of the lakes and drill. Okay, so this is honest to God drilling sediments. You know, this is getting further away from what I'm. And we measured the trace elements. So it's a Fred type series of measurements where you can get, you know, using the really high precision measurements, you can measure the change in the concentrations, and you can see with time that when you get towards the Industrial Revolution, bam, they use the uranium enrichment factor, but you can use almost anything and it goes up. So when we look at the sulfur isotopes, what we see is when you're diluting with a lot of man-made dust, it's all normal. But before that time, when there's not man-made activity, the natural background, probably not from people, is isotopically anomalous. So it says more that there's activity, the background of the Earth is anomalous, and it shows up over time in the older times in the 1800s. So we need to go back and hit another lake or two and get a little bit further back to see what the natural variation might be on a 1,000-year time scale. It's a little hard because you got to schlep all this stuff up on a yak to drill up there, but that's life. So that's what we're trying to understand. And the other part that we don't understand is this idea of the sulfur plus sulfur. Are there other reactions that we don't know about? And the sulfur cycle is really complicated, especially in the archean. This is a figure by Jim Casting. And in some of the processes, this reaction goes. Sulfur plus S2 goes to S3. Well, the anomaly that we found in oxygen is O plus O2. The first mass-independent anomaly was ozone formation. And S plus S2 is exactly the same reaction, right? Sulfur lies right under oxygen. It's isoelectronic. So this reaction, in theory, should be mass independent. But the question is, can you predict it? So, yeah, this is my picture of cold dark matter. Okay, so that has nothing to do with anything. It's just segue. So trying to understand what that sulfur reaction might be and we might not accounting for it, then we have to flip to what we know better to compare it to, which is O plus O2. And this story starts in the meteorite world with Bob Clayton. And when he measured the oxygen isotopes, so here's oxygen 1716 and this is 1816, and this is the so-called terrestrial line, even though it's called the terrestrial line, even though every species in the entire atmosphere doesn't lie on this line. This is the terrestrial line. It's the bulk rock line, basically. And this is the high temperature inclusions, calcium, aluminum inclusions in Allende. And it defines a line of about slope 1. And it was originally thought that it was supernova. The fact is, this is another one of those that no one agrees. And so we're trying to understand, are there chemical reactions that can give you this? And the answer is yes. If you make ozone, if you start here and you make ozone, here's at 17 and 18, it's the same. It's exactly the same slope. No difference at all. That's it. So the question is, when I found this is my first experiment, they gave me, instead of money, they gave me Urey's old mass spectrometer, and I rebuilt it to measure oxygen isotopes after I told him I was going to rebuild his machine, and I got permission to do it and did it. I found this, and I thought at the time, I said, this is so simple, you get a slope, okay, fine, whatever. If the ozone formation goes, it seems like this should be simple. This was the easiest possible and also the cheapest experiment that I could envision doing to test whether you can produce a mass-independent effect that looks like the meteorites. And basically, all you do is break apart O2. It forms a transition state that lives about 100 femtoseconds, 120 if you're really counting. Femtoseconds is the lifetime. And then it stabilizes, or it falls back apart again. In that stabilization, there's a preference based on symmetry. The community in chemical physics agrees that it's symmetry-based. No one argues about this anymore. And that's because whether it's a 17 or 18 on the end, it behaves differently than its pure 16. It's a rotational symmetry, right? You have twice as many states if it's asymmetric, because you flip it, it's a different guy. And so these guys behave equally, which is why it's a slope 1. And different than this, and preferential for this. So this goes up positive slope 1, and this goes negative slope 1, to which you start with. And it's based on symmetry. But we don't understand it. Now you're thinking, Mark, you did this as an assistant professor. That means that, there were still like pterodactyls alive and stuff like that. It's a long time ago. But the fact is, we can't. This is the only chemical reaction in the whole world where you can know everything about the chemical reaction. It's the only one. The D plus H2 going to H plus HD. In the whole chemical community, there was 4 tied up in trying to understand this reaction. And it's hideously complicated. It's the only reaction you can understand. Think of it this way. All right, you got a deuterium here. Chemistry is electrons, right? That's what, I live in a chemistry department, and even though I'm not really a chemist, and you have 1 electron here, and it's H2, you have 2 electrons, 3 stinking electrons. And that's the best you can do is 3 electrons. So imagine you want to understand a chemical reaction with something like oxygen or nitrogen with 7 electrons. Forget it. It can't be done computationally. You can only do it for this. And if you do all the potential energy in 3-dimensional surfaces, it gets to be hideously complicated. This is for the simplest system there is for a reaction. It's the energy surfaces with a stable here, repulsive curves, and all that. So, and it has to do with when an atom and a molecule come together, they have to stabilize. And if it doesn't stabilize and get to the bottom here, it breaks. And so in that selection, it cares if it's symmetric or not. There's more pathways for it. But the problem is you have to know the pathways from the excited state to the ground state, and you can't calculate them. It's too complicated for state of the art. You could do it. The guy who does this, I'm going to show you a picture of what you do. is that if you take a normal potential energy surface and let the O and O2 come together and fall in here, or dissociate and fall out. Remember when I said that it's not just a matter of climbing up this well. You can calculate it. To do this by computational means, it would take on the order of 10 to the 7th years to calculate it. And that's a pretty big budget on a supercomputer to have 10 million years of time. And you still end up having to make approximations. But what it looks like is when you pump energy in and you have 3 atoms of ozone in this case, and then you add energy. Now you see it's going up here, and here we are coming up out of that well at the bottom, and you're getting up to the top where the action is in a dissociation or combination. It starts looking like this. And so what it is those 3 oxygen atoms, and these are the electron configurations, and this is where it's stable. It has to climb up to here, and this is where he has to cut the calculation off because he runs out of money, basically. And so what it means is, if you're looking at the stable part and you're an O and O2 coming together, you have to end up here, is you have channels. So the symmetric guys don't have the restriction and they combine to make ozone, but the asymmetric guys can't slide down here as easily to be stabilized. This is what you have to worry about to calculate it. And you can't calculate it for ozone. So the only thing you can do is measure it. And the same is true for the things that are interesting for meteorites, which is what I want to end up with here. So like I said, oxygen, we know it's O plus O2 in its symmetry. So if I form an OSIO like an OO2, the oxygens are the end. That's the important part. Who's on the end? And you're all geologists, geophysics, geochemists, or some blend, except for me. And so it cares who's on the end because of the symmetry group, and it doesn't care who's in the middle. That makes it pretty general. SiO4 is unique, right? That's why you can make rocks out of silicates. It's really unique geochemically. But sulfur is the same. So it's possible that this reaction is like this reaction. We just can't calculate it. It needs to be measured, or reactions like that, to see if that's the source of the anomaly in the Precambrian, and to tell us more about this. But for the meteorite source, this is where I'm going to get to where it's experimental and new and don't understand it, is that means that if you started with a gas phase molecule, in interstellar space, if you're a radio astronomer, you look and see where is silicon, right? Fred's written a number of papers in the last 3 or 4 years on silicon. Silicon is really interesting what it does in planetary accretion and differentiation. Where does it go and what does it do? If you started out in the very beginning, and before it gets to be a nebula, it's mostly tied up here. And in some parts, you got to go to SiO2 and then to an SiO4. So is that step the magic chemistry step that gives you the anomaly? And so we did one step. I talked about it last time, so I'll just go through it. As a result of the Genesis experiment, we learned how to control plumes with a laser, where you vaporize a solid and make a gas phase plume. So we learned how to make an SiO gas that we could react with O2 or OH, and then see if the solid is mass independent because of a symmetry rule. In which case, if we get something that looks like the meteorites, we're a step closer to people that are respected meteorite people would be interested in. Because at the end of the day, you don't give a crap about ozone. I mean, seriously, there is no ozone in the nebula. But if it's going from a gas to a particle, and the particle ends up being at the heart of a CAI or something, all right, that's a bit more interesting. So we did these experiments to start learning how to do it, vaporizing it in the machine that we built for Genesis to measure oxygen and sulfur. And it's connected straight to the mass spectrometer where we can fluorinate it and straight into the mass spectrometer. And what we find in this plume is that you have 2 oxidation pathways you have to worry about. One is this one, SiO plus OH, and this one, SiO plus O. All the rate constants are known. So we can measure this with a pure oxygen system, so we know the isotope effect with this. It's normal. So when we add hydrogen, we make this reaction go. And then we can calculate by difference in the system, subtract off this effect, and only leave you with the isotope effect associated with SiO plus OH. The dominant reactant in a solar nebula to add oxygen is OH. It goes that way because you have an excess of 10 to the third or more of hydrogen. And anytime you get an oxygen atom or a free oxygen around, it ends up making OH. It just does. There's so much OH that there's, in some of the interstellar molecular clouds, there's SiO masers and OH masers, just because there's so much. When it gets stimulated, it mazes, I should say. So this is a paper 3 years ago in Science, I think I can't remember. So if you calculate it, the slope that you get in the product SiO2 is this, slope of 1. Here's the oxygen we start with. Here's the oxygen we start with, and here's the SiO we start with, and here's the bulk. So what you find is the best fit line goes through the bulk, and that's the data points that you calculate for the SiO plus OH. It's a slope of 1. Okay, it's not bad. But I know what you're thinking. You're thinking, yeah, Mark, but it's fair. It's normal chemical kinetics. You calculated it. So how do I know there wasn't something up your sleeve? You know, you like these guys when you go to Montmartre with the ball under the 3 buckets, and you move it around like this. How do you know you didn't do that to me? And you moved the ball and you slipped it up your sleeve. How do I know that you didn't do that? Okay, fine. I agree with you. It seems like I could have pulled a fast one. So I got to do another experiment. Subrata Chakraborty did this. That has no assumptions in it. Plain and simple. And you'll agree, no, there's no 3-card Monte. That's what they call it in Chicago, when you do the 3 cards, choose the ace. So we did a different set of experiments. This is dirt simple. This is as simple as it can be. So we take SiO. How am I doing? Good, I'll finish it just when I wanted to. This is the last part. This isn't published. So you take SiO, and we had to build Roger will appreciate this. One of the things we had to get out of this is you have to be able to go up to 1800 Kelvin in a very controlled way with a known amount of SiO and not burn the damn thing out, and do it in a vacuum so you can get a controlled plume of SiO. And what we have above it, I can't quite see from here, but you got the heater, and then you've got this. It's a plate. And what this wrapping is, it's a liquid nitrogen coil. And then this whole thing goes into a vacuum chamber that we pump down at before we start to about 10 to the minus 9. This is a really good vacuum chamber. And then we heat the SiO up with this cold, and what does it do? It plates SiO across the surface. Nice, clean chemical vapor deposition, just like they do in Silicon Valley. It's actually that's actually where I got the literature from to learn how to do this. So we get a pure layer of SiO. We turn off the SiO, and then we let in water. Small amount, but water. And this is at liquid nitrogen temperature, so it freezes a layer of water onto the SiO. Turn off the water, pump everything away, leaving it frozen, and let it sit. That's the experiment, nothing else. There's no photons of light, just that. Let it sit. And then with time, we do an experiment. We took it out after an hour. Then we take it out after 2, 3, 4, 5 hours and measure the solid that's left behind with only SiO and OH and water in the presence of each other. See, there's another picture of what it looks like. It's simple. It's just that to get the stupid thing to work took about 2 years of futzing around to learn how to control temperature the way we want. And we can measure the temperature optically, with a radiometer. So if somebody wants to know what the temperature is, we know, we can measure it. You can buy something at Home Depot to measure these things now. And so it's just plated out here. So here's what it looks like. You can see it makes a nice thin film. There's what the film looks like. I took this picture with a confocal, and that's what it looks like. All right, so it's an SiO surface, and that's where the water freezes onto this. That's all it is. And I even did SEM work. I mean, I got to tell you, after going to LPSC for 40 years, I've seen 5.5 million SEM pictures. So I'm so proud I get to show my own for once. So we know the stoichiometry, right? It's no big deal. We look at and it's basically SiO 1.2 right away. It's oxidized a little bit, but not a lot. Here, you can see the stoichiometry of it. And then with time, it grows, And here is the product, the first three that we measured. There's now a number more. And look, it lies on a slope. It's got a little error in it because it doesn't make a lot of product, of about a slope of 1, just like the other experiment. And it goes through the bulk. And there's no assumptions. We measure the SiO vapor product, and we measure the SiO that we start with, and it goes through the bulk, and it's a slope of 1. And there's no photons. It's only ice and it's SiO, nothing else. So now we let it go with time. So when there's a time progression, after 1 hour, we've turned off the liquid nitrogen flow. So it starts to warm up till it gets to room temperature. So at 1 hour, 2.5, up to 27 hours. Here's the capital oxygen 17 from a series 1, 2, 3, 4, 5 of them. And look, you can see it's oxidizing. And look, you can see with time, the morphology and the chemistry changes, and it gives you a slope 1 effect, and it's only water. There's no assumptions in this. This is it. Look, there's nothing under the can. There's no ball hidden up in my sleeve. That's all it is. So how do you explain it? Okay. So the answer is I don't know for sure, but there's an enormous literature in solid-state physics because of the electronic industry that uses water layers to understand the surface chemistry and physics on new surfaces. Water, and ice especially, reacts and dissociates. Okay, well, how the hell does that happen? It's not like water is not a strong bond. It's a very strong bond. So what happens is you have the normal matrix in material, and the silicon and oxygen sit together. If you get a defect, like when you break a mineral surface, or you don't have a pure mineral surface, you have dangling bonds. They're in the physics community, you call it a point defect group. I think it's the same in geochemistry too. And the point defect then has a band gap. It's the Fermi levels between the conduction band, which is the negative, and the hole pair behind. And that hole, or the electron in the conduction band, allows you to pass an electron from the bond that's broken and free, that normally was broken, now it's just free silicon or free oxygen. That E- will react with the water or ice around it and dissociate the water. And it dissociates the water and makes OH. And the OH reacts with the SiO, and boom, it's the symmetry dependence going to SiO2. We measure the stoichiometry of it. We watch it grow. It goes along the slope 1 line, and it's growing. But the energy for the reaction isn't provided by photons. It's the chemistry of oxidation of the reduced silicon species in oxidizing its way up to SiO2. And that's all it is. The problem, the physics of it is incredibly interesting. I like it a lot. This is what I think goes on in this, is you use the band gap. And there's a number of minerals that have the right band gap, but it gives you the right slope. It's consistent with the symmetry argument and the association, but the energy is provided by the defects in the mineral itself, because that's all there is. There's no cheating in the measurements. They're reproducible. It oxidizes the stoichiometry we measure. There's nothing missing in the experiments. There's no unknowns at all, but it's a slope 1. So the next question is, and I can imagine Roger getting ready to ask me this, is yeah, but it's just quartz. I want something that I can get my hands on. I want a silicate, or I want something besides just silicon. So this is all on the surface. As I say, here's the one that we published in Science where we make the OH, but people didn't like it because you had to model it. Okay, fine. I bought I thought it was excessive, but nonetheless, I bought it. So now you do it and you still get the same thing, and it goes through the bulk composition. So what we've done next, as of when I got on a plane to come to France, is to vaporize the SiO along with one of the early condensates, corundum, Al2O3, to start our way towards what we really care about is an aluminosilicate. And yes, calcium would be in there too. but start to see. But if you look at the texture of what the aluminum silicate looks like compared to what the SiO2 looks like, it's completely different. So something's going on differently in these reactions. So besides, we haven't measured the isotopes. I know what you're going to think. We haven't measured it. We just got this literally as I was leaving. So we're doing this now. But by looking at this, looking at the stoichiometry, we can at least begin to understand how do you go from a gas to a solid in a solar nebula. Anybody that works in a meteor, at some point, we've never worried about this, but at some point we have to figure that out. So this is the first step in the basic physical chemistry to try to understand how do you go from a gas to a solid, and do I have to worry about the chemistry and the physics of the process? And the answer is, yeah, probably. If the oxygen anomaly gives you a slope 1 just by the oxidation process in the presence of ice or water, I hadn't expected that, right? I didn't order that on the menu, but that's what came out of it. And so we don't know at this point. We just don't. But the experiments are right. There's no problem with the experiments, and that's what it gives. So we'll work our way up to something like a CAI, but begin to understand each step in it, so that when we're looking at when I read a Roger paper or a Fred paper at the meteorite papers and they're measuring things in meteorites, then I can try to see, is there a way I can jump from this to them and try to understand it and the isotopes at the same time. I mean, it's just a start. No one's ever looked at this with the detail where you could understand the reaction chemical physics, but we've got all the quantum mechanics behind the reaction. So it's not some flimsy thing. We're using state-of-the-art quantum theory to figure out the source of the effects and the symmetry dependence, but then trying to understand how the heck do you make the solid. And it turns out it's pretty interesting. The problem has always been it's just really hard to do the reaction right. It's not, because basically what everyone does is you heat it and you plop. You vaporize it and it condensates, but there's no real chemistry in there. You have to leave it diffuse enough like it is in a nebula so that it can do a real chemical reaction in the gas phase, and that's the hard part. So that's all I have to tell you, but that's what we're trying to do. The advantage of doing this is we don't have to play the game then of, well, do I mix one part here to 1 part butter, 1 part chocolate to get all the different meteorites? If it's coming from a single reservoir, it's a lot easier. The Earth's atmosphere, by the way, looks like this, except turned upside down. You have the slope 1 line coming up through ozone. All of the oxygen species in the atmosphere do this in the same place and time, in the air that you're breathing. I should put a plot of this in, I didn't. If you look at the sulfate, nitrate, peroxide, O2, O2 is anomalous, by the way, it looks like this, but flip it over, because ozone is the product instead of the CAI, and it varies a bit with the size of the reservoir. So you can produce multiple reservoirs in 1 cubic centimeter right now. There's nitrate in this volume here, and sulfate, and it's all anomalous, just like this. So you can do it, it's done, nature's already done it. So now I will try to understand, to get that perspective. So that's where we are. So I'm going to end with this picture. If you want to see the real picture, you know where it is. It's across the river. You can go and see it if you can find the room. The Louvre is not always easy to find things. The only thing worse is the cemetery, the old one. I went to see, I'm the right age that I had to at least go see where Jim Morrison was buried. That's harder to find than anything in the Louvre, because at least the maps are right in the Louvre. So this is called the astronomer, thinking about space and time. So that's what I did today, was go back through time, starting, between the early solar system, what's done in the early solar system that's photochemical, ending with what's done in the older solar system that probably isn't photochemical. The Archean record, going back from 3.8-ish to, say, 2.2 in the sulfur anomalies, tied up in this same business of trying to understand the chemical reaction, where there's pieces that I don't understand. So there's a lot we don't understand, but we're really making progress in the basics. And thank you for the invitation to come here. It's been nice to visit, as always. Questions are fine as long as they're easy. It's lunchtime. Yep. There you go.
Yeah. So, I guess it's just the beginning of these experiments, but what do you think? Maybe I missed that, but is there any, what is the relation with temperature in terms of these effects that you see? Because I see the experiments at a very low temperature, right?
Room temperature.
Room temperature.
Well, depending on your perspective, room temperature. But
when you go to the CDI, this will happen at very high temperature.
Shouldn't matter. It's a symmetry dependence. And where it comes in quantum mechanically, at those levels, it doesn't affect it.
There is no temperature.
There should be maybe a small one, but it may increase the effect with higher temperature. Normally, it goes the opposite way. We know this from ozone. At higher temperature, the effect is bigger. There's a reason for it, but it has to do with the quantum mechanics of the states connecting with each other, and they do it better at high temperature. So it's the reverse of everything we learned for isotope effects. Cold is big. It's the other way around here.
But if you do it at low temperature like that, there is no specificity to have it on meteorites. It requires more specific condition, like condensing the gas at high temperature and so on. So you should find it everywhere else, no?
Yeah, all right. So I wasn't going to talk about it because I didn't want to confess to being wrong. But here, one of my students, Morgan Nunn, her thesis was looking at water in meteorites and lunar samples. And it's a stepwise release that you look at just like with noble gases, you do a stepwise release of the water, fluorinated, and measure the oxygen. And so we work through the normal classes of meteorite, we work through the moon, and the moon is really interesting, or trying to publish it or write it up now, or getting it written up now. But in the process, of course, you say, well, what do you standardize to? So I got some samples from a friend of mine at Scripps, who's a real geologist, not like me. He gave me some basalts from Iceland, and he measured it. We ground it up, did the terrestrial samples to look at the oxygen in the terrestrial samples, and it was all anomalous. So he said, damn, let's do it again. Did it again, it's anomalous. He said, all right, throw that damn rock away. Give us one of the other ones he gave us. It's all anomalous. So I went down to Scripps and talked to the student. I said, where'd you get this stupid sample? What'd you do? Were you playing around with ozone? What is this? He says, what do you mean? It's from Iceland. I said, well, it's a basalt? I said, I'm not a geologist, but I know what basalts are. They come out hot and they cool off, and that's the end of it. That's their life story. What happened? He says, that's it. I said, there's nothing else. He said, well, it was under ice for maybe a period of a glacier, but it's exposed to ice. So as we measured more and more terrestrial samples, it's anomalous on the surfaces. Not the whole rock, mind you, but it's anomalous in this. If we take another sample that hasn't been exposed to it, like sand from the beach, we're in La Jolla, so it's easy. It's normal. The water comes off of it normal, but because there's no point, they're all polished, right? So all of the beach type silicates and mixed rocks that you get in there, it comes out normal. So in some environments you get it and some you don't. When we measure samples like the, what the hell do they call it? The synthetic lunar samples. Well, they're not really synthetic lunar samples. They're actually Arizona dirt that they've cleaned up, and they get Mars simulants this way. They too have anomalous water in it. So the answer is, I don't know, but it does show up in nature. How broad it is, it shows up in aerosols. We've seen it in aerosols in the carbonates, and that they get from the water. But it may be the same thing. But you're right. You would expect with an ocean and a bottom of an ocean, you would expect it everywhere. So, that's all I know as of October 20th. They're hungry. It's lunchtime. Thank you.